Okay. Yes. So I also want to talk about. Okay. Say it again. TEMP. Yep. ERATURE. Yeah. I want to say temperature. It's more fancy. So what do you know what a temperature is? Imagine you don't know anything about that. Because that's on a molecular scale. We haven't done that yet. So what is a temperature? Yes. When you touch something, what do you feel? That is what temperature, that is the fundamental definition of what temperature is. A temperature is how hot or cold something feels to us. That is also called the operational definition of what temperature is. So the operational definition of what temperature is how hot or cold something feels to us. Because of course, we are the most important things on the planet. I am the most important person to me. I have to feel good. And that is what temperature is. Okay? So now the next question is, how do I show how I feel? We have to have a measurement device to tell me how hot or cold it is. That's what thermal equilibrium came into existence. So when you take your temperature, how does a doctor take your temperature? I'm not talking about those fancy digital ones, the old one. What did they have to do? That's where the concept of thermal equilibrium comes in. So in olden times, when I was a child, I don't know if you guys remember that, but they used to take a thermometer and stick it in under your tongue to measure your temperature. And what would the doctor say? You have to keep it in for a minute. Why a minute?
So that way the thermometer can reach
the same temperature as your body does. The fancy word for that is called thermal equilibrium. Do you see how it develops? So whatever fancy word scientists use for stuff, fundamentally is how we have come up with things. Right? And things make sense once you understand them. So what is the thermometer doing? It is taking that long to reach, now this is fancy word, right? To reach thermal equilibrium with its surrounding, which is now your tongue and your body. Make sense? There also is a really cool thing we have here. And if you guys are promised to be gentle with it, I'll show it to you. No one drop it, but this is the only one we have. It's very gentle. Very, please, can we please be extremely gentle with this. But here's how it works. Why do you think that is happening? Can you guys see it on Zoom? No? I'll hold it up. Can you guys see it now? Okay, I'm going to hold it. Why do you think this is happening? There's a little man in there who's pumping it? Yes. And he's called Maxwell's demon. We'll get to Maxwell's demon. This liquid that's in here is boiling with my hand, the temperature of my hand. It boils and goes to the other side because it reaches thermal equilibrium with my hand very quickly. And the boiling temperature of this is the same temperature as my hand, about 98 Fahrenheit. And it actually boils and is boiling to the other side.
So there's a little bit of pressure.
I should not be exerting any pressure.
Right, but
It's not water.
okay.
It's a special liquid. Isn't that fascinating? So cool, right? This is so cool. Okay, and you guys can all come and not apply pressure to it later.
Yes, but the pressure is all internal.
Right, internal.
External.
So don't apply any force to it or anything, right? This is very, very, very delicate. But it is such a good demonstration of what it means to be in thermal equilibrium. Now that we understand it, we now have to be physicists and write good words. Okay, so what is temperature? No. Most fundamental definition is something you measure with a thermometer. That's cyclic. And I haven't actually told you anything. I've told you it's something that you measure with a thermometer. But I haven't told you what a thermometer is. It's something that measures temperature. Woohoo! That's catch-22. Right? So now we have to come up with a measure with a device that I'm going to call a thermometer. So what is a thermometer? Well, a thermometer is something that has the following properties. Number one, it should measure temperature of the object it is in contact with. And how does it do that? By reaching thermal equilibrium with it in a certain time. And that certain time has a name associated with it. That's called the relaxation time. Number two, there must be a property of the material that you are using that varies linearly with the change in temperature. So the word linearly is very important in the range under consideration. So you must be able to trust that in the range you are looking at, your material that you are using to make your thermometer varies linearly, whether it's expanding or contracting, with the temperature range you're looking at. So for example, mercury is a very good thermometer in the normal range that humans need. From 72 to 76, what does mercury do? Well, what is it doing? It is rising, but what is it doing? Expanding, right? That word. But what happens when it goes from 72 to 68?
Tracks.
Right. But what about the same if it goes from 72 to 71? Exponentially. Get it? So it has to be a linear expansion or a contraction. It couldn't be that when it contracts from 45 to 75, it has a different value. And then when it goes from 45 to 32, it has a different value. Does that make sense?
Yes.
That word linearly is very important, right? Proportionally, it has to expand and or contract. Got it? Okay, number 3. There must be a visible, predefined scale where an observer must observe. There must be a visible, predefined scale where an observer can visualize the expansion and contraction of the material. Now, what can possibly be those materials that we can use? We can use solids. Do you guys know how your thermal ACs and heaters work? Not quite. What they do is they have like little tiny strips divided into 2. This one has a different expansion coefficient and this one has a different expansion coefficient, and they're stuck together. Wait, hold on. They're kind of stuck together. When it gets too hot, this expands and hits this side and it cools the area. When it gets too cold, this expands and hits this side and heats the area. I think they're called bimetallic strips. They have different expansion coefficients depending on whether it's hot or cold. So what else can we use? So solids can be used. Liquids, we already know they can be used, right? Is water a good thing to use for expansion and contraction?
Depends on your range.
Exactly. What if you go over 100? Or go under 0 degrees Celsius? Won't work. Mercury, on the other hand, works really well. Gases can also be used, right? Gas thermometers can also be used because of that property that you were talking about, kinetic energy. They hit more things as they go up, but they're harder to make and harder to maintain and blah, blah, blah.